cylinder, right just means that it's straight up and down. My screen sound, is it? Here we go. So right just means that straight up and down. It's not like a slanted one, which you almost would never have like in real life anyway, right? Or not in a lot of contexts. Not for a tank anyway, right? So the radius of the tank is 8 meters and the height of the tank is 10 meters. The tank is being drained at a rate of 50 meters cubed per hour. At what rate is the height of the water level changing? Okay, so we have, for this, we need to write the equation of the area of the volume of the shape. So for a cylinder, any type of a cylinder or a prism, right? So like a cylinder, a rectangular prism, triangular prism, anything where you basically have like a base and then straight sides going up. Then our volume is the area of the base of the figure times the height. How do we find the area of the base for a cylinder? Pi r squared, because the base is a circle, right? So our volume formula is going to be pi r squared times height. And so that is our equation that we'll be working from here. We are supposed to identify the variables from the equations and determine if quantities are constant or changing. So the problem says the radius of the tank is 8 meters. And it gives us the height of the tank is 10 meters. And then it tells us that the tank is being drained at a rate of 50 meters cubed. Now, it would appear like we got some constant things here, but we're not looking at like the volume of the cylinder changing. We're looking at the water in the cylinder, right? So what we're really thinking about is the volume of this water right here, not the volume of the whole cylinder. So for that water, I could think about this as like my height of that water. But what's the radius of the water? Does it ever change? No, it's just going like a cylinder draining, the radius doesn't change. So the radius is still 8 meters here, right? So the height will be changing because the height of the tank itself is not going to change. But we're talking about the water in the tank is what we're concerned with, right? So the height of the water in the tank will change as we see this tank being drained, but the radius does not change. So our constants here, our radius equals 8 at all times. And then we do have the tank is being drained at a rate of 50 cubic meters per hour. So what is that as far as variables go? It's a rate, so it's a d something dt. It's dv dt is, now watch this, the water is being drained. So is that rate positive or negative? Negative, because the volume is decreasing, so it's negative 50. Negative 50 meters cubed per hour. Okay, so obviously you can't plug in dv dt before you take the derivative because it's not there, but you can plug in r before you take the derivative. Changing, our variable that's changing here is our height. The height of the water is going to change. And volume is also going to change. Right? So you should see all of your variables in your equation, v, r, and h. They should all be here somewhere, right? They're either over here where they're changing, or they're over here where they're constant, and we know what they are at all times, not just at an instant, but at all times. There. Then we need to think about what we're finding, and we want to determine, at what rate is the height of the water changing? So what are we finding? The rate, the height that's changing. When you see that word rate, you're thinking d something dt. So it's height, so it's dh dt. Now this problem is a little bit different than some of the other problems that we have seen, because it doesn't say at like time equals 5 or when the height is 7, right? Because usually we say find dh dt when h equals 4. So that may or may not end up being an issue for us, but we just don't have it, so we're not going to write it down right now. Okay? So step 3 had been like a piece that we did not use on the notes that we were doing yesterday, right? We did not do this. But we have a constant value right here that stays the same no matter what. That can be plugged into the equation before we take the derivative. Okay? So, plug any constants into the equation before differentiating, if applicable. It's applicable here. So our volume formula is going to be pi times h squared times height. And let's simplify that a little bit. 8 squared is 64, so I'm going to make this 64 pi times h. Now that makes things a lot easier, because this is a very, very simple derivative for us to take here. Now, it does say convert equation to one variable if necessary. Not necessary here because h is our only variable on the right-hand side, right? So now we're just going to take the derivative like we did on all of these others. So dv dt equals 64 pi, just a constant, right? So the derivative of 64 pi times h is just 64 pi. The h goes away, right, because it has an exponent of 1, and we're subtracting 1 from the exponent there. But what else do I need with this? dh dt.
So are we not going to use the higher the tank is 10 meters at all?
We are not using it at all. No, it doesn't come into play. And on cylinder problems, that's usually the case. It's extra information they're trying to get you to plug it in somewhere, but it really doesn't need to be plugged in. There. So we've got our derivative. Everything looks good. Also, notice what just happened. H is gone. So they didn't give us like a height to plug in, but do we need a height to plug in? We do not. So actually it doesn't really matter here whether or not our height is 7 or 10 or 2, right? So we're going to plug in all values from step 2. We are going to plug in dv dt, which is negative 50. And we got 64 pi. And then we don't have anything else to plug in, right? But that's okay because the h dt is what we're looking for anyway, right? The h dt is what we're looking for anyway. So we just have to solve. And to solve for dh dt, we just divide by 64 pi. It'll reduce there we'll definitely go negative 25 over, let's see, half of 64 is 32. There. We want to put units with this. It doesn't reduce anymore, does it? 25 over 32. No. I'm also just going to get a decimal for that because really, in context of water tanks, we'd really rather just have a decimal than this exact answer, right? So that is negative 0.6 2.248868 right there. Units, think dV dt, change in volume over change in time. How are we measuring volume for this problem? Meters cubed, because volume is going to be cubic meters, right? So meters cubed per, and then our time was hours. Oh, it's H, isn't it? Oh, yeah. You're right. I'm wrong. This is not dV/dt. I'm just slapping things down that aren't true. What were we solving for? The H dt, in which case my units are not cubic meters. They are just meters per hour. That looks better. Yes. Yes, definitely. And I would not even attempt to simplify any of that, because there's no extra credit for simplifying, and you might mess it up. So you could see it either way on these. Now, in this particular case, your volume is changing at a constant rate, and your height is also changing at a constant rate. So if you, for some reason, need to know what that rate is that the height is dropping, you would be able to find that. And both are going to be constant in this case. But let's look at different contexts. In this case, a block of ice is in the shape of a square prism. The original dimensions of the block of ice are 4 by 4 by 8. As the ice cube melts, it retains the property that its height is twice the length of one side of its square base. So it's like melting in proportion, right? You're keeping the same shape, but it's, smaller. If x is decreasing at a constant rate of 0.1 feet per hour, at what rate is the volume of the ice cube decreasing when x equals 0.5 feet? Okay, so they do tell us that the square base, the length of the side of the square base is x, right? So I'm going to call this x, which if this is x, then this is also x right here. And then I'm going to call the height over here h. So, and that, we could say length times width times height. But by changing both of these to x, which are our square base, it reduces one of the variables that we have. We're still going to have 3 variables in the problem, but we don't have that 4th one, right? Because the length and width are the same. So, yes. I'm going to wait till a little bit later to do that, but if you wanted to go ahead and do that at this point, it would make my step 4 that I have unnecessary. So yes, you could go ahead and take that and do that in this case. So our volume is x times h, which is x squared times h. Okay, so we want to identify the variables. In fact, if you do go ahead and make it 2x, it does cut down a little bit on what you have to do. So I know the x is 4 and the h is 8, but do they stay 4 and 8? They do not. So both x and h are changing, which means volume's got to be changing too. So changing, I've got all 3 of my variables, v, x, and h. So am I going to be able to plug any numbers in before I take the derivative? I will not on this problem. Our constant, we do have a constant, and And that constant is the rate at which our x is changing. So x is decreasing at a constant rate of 0.1 feet per hour. So variable-wise, what is that going to be? Something dt. What is it? Dx dt. So dx dt is going to be negative 0.1 feet per hour. Okay, and we are finding, okay, at what rate is the volume of the ice decreasing. So what's that one going to be? D what? dt? dv? dt. And notice this one does give us when x equals 0.5. So, step 3, I have it in red up here. We can't actually do step 3. There are no constants to plug in. X, H, and V are all changing. Now, in this case, this is the first one we've seen. I've got 2 variables that are in my function, right? So I've got, well, 3 if you want to count the V. But on the right-hand side of this function, I've got 2 variables to consider. So I've got an x squared and an h. And our life is going to be very difficult. If we have to take that derivative, it would require a product rule. It's going to mean we got a dx dt and a dh dt. Do we know anything about dh dt? We don't know it. So if we have a dh dt, we would have to set up some other type of formula to try to find dh dt. I don't even know if it's possible, but if it is, we don't want to do it, right? So in most cases, you can come up with a way to replace one of the variables so that you only have one variable in the problem. And we're going to do what Connor suggested there at the beginning. You could go ahead and do it if you want there, but they tell us that this ice cube retains the property that height is twice the length of one side of the square base, which we're calling x. So height, h, equals 2x, right? So we know that h equals 2x. So in that volume formula, which is x squared times h, I could replace h with 2x. And then that means now my volume formula is 2x to the third. Now that looks pretty easy to take the derivative of, right? That's nice and friendly now. So if you can get to this point, the problems should be pretty straightforward for them. It's going to be a derivative. It's going to be plugging in. Most of the time, the derivative doesn't even require a lot of special rules. But you got to get to this point first. That's the hard part. So now we just take the derivative. dv dt is going to be 6x squared dx dt. We're going to plug in all the numbers that we know from step 2, which were that dx dt is always negative 0.1, and we're trying to find dv dt, so we're not plugging in for it, but we know that we're looking at the point when x equals 0.5, so we are going to have dv dt is going to equal 6 times, I'm going to use a fraction instead of the 0.5. Do what you will, but I think it's easier, particularly if it's calculator inactive. And then I've got negative 0.1. I'm going to go negative 1/10 on that right there. Again, if you're more of a decimal person, go for it. There, and then we just have to simplify. So we're looking at 6 times 1/4 times negative 1/10. Put that 6 over 1. So you're getting negative 6 over 40. That will reduce to negative 3 over 20 right there. So we get dv dt equals -3 over 20. And for our units, we're talking volume, which is cubic units, which, what were we measuring in? Feet. So we got cubic feet, and then dt is time. That is hours for this problem. So when the ice cube has melted all the way down to where it only has a base that is 1/2 of a foot by 1/2 of a foot, the ice is melting at a rate of -3 over 20 square feet or cubic feet per hour. Okay, questions so far? All right. Let's see how much more I got a cone right here. Oh yeah, we got to do a cone problem. So I will be surprised if you do not see some type of cone problem that is a related rate on the exam. Somewhere. Multiple choice, free response. It's a very common type of problem for them to give you because it is going to have you do a lot of different things with the graph. So, a cone has a height of 14 feet and a radius of 5 feet. Water is being drained from the tank at a rate of 3 cubic feet per minute. How fast is the water level dropping when the water level is 6 feet? Okay, so in this case, we have, again, much like the cylinder tank, we're draining the tank, but we're concerned with water level, right? Like we want to know, like, you know, we got the water dropping. So we want to know about like the volume of the water in the tank. The tank itself, the radius and the height are not changing. But whenever we look at the volume, we're talking about the volume of the water. So in this case, the radius of this tank is 5 feet. And the height of this tank here is 14 feet. But the radius of the water level, is it equal to 5 feet? Only whenever the tank is full, right? And the height, is it equal to 14 feet? Only when the tank is full, right? So R and H in this case are both changing. In the cylinder, the sides are straight. The radius doesn't change. Makes the problem a lot easier. For this type of problem, we're going to run through our steps. We're going to start with our volume formula. Anybody remember the volume of a cone? Yes, 1/3 pi r squared times h. Remember, cylinder that we just did was the area of the base, pi r squared, times the height, right? And I did not teach you guys for Math 3 when we do volume stuff. Anybody ever shown you, filled up a cone? I may have done it sometime. I don't know. I've done it lots of times teaching, but I don't think I did it for you guys. But I love to. I may have done it in pre-cal, actually. I'm not certain. Who knows?
I think that you build up like a pyramid in a cone or something.
Yeah, pyramid will be the same. Yeah. So at least there's a vague memory. Maybe somebody. I probably did it. And sometimes my husband mentions things that have happened.
Something about showing us that a pyramid and a cone are the same volume.
Yeah, the pyramid and the cone have the same volume formula because it takes 3 of them to fill up a cylinder of the same height and radius, right? So I always love doing that because it would not be my guess. And most of the time I make everybody guess first, and most people guess 2, or maybe 1.5 or 2.5, but not that many people usually guess that it takes 3 of the cones to fill up the same cylinder with the height and the radius the same. But it takes 3 cones to fill up 1 cylinder, so your formula is just 1/3 of the cylinder there. most of the time they're going to give you the formula. Hopefully they'll give you the formula, but it doesn't hurt to know it just in case. There's no guarantees. AP does not have a list of, we will give you these formulas. Like I said, they almost never give you 2D formulas. They usually give you 3D formulas, except for rectangular prisms, which are just length times width times height. So, we're going to identify the variables from the equation. So changing here, and again, like, you don't have to write this down every time, but I think it helps a little bit for you to think about what's happening. So as that water drains, radius and height, they're both changing, because as the water drains, that like surface of the areas of the water is getting smaller and smaller. So radius and height, they're both changing, which means volume definitely has to be changing. So you're not going to have any numbers that you can plug in before you take the derivative. Constant is going to be the rate at which water is being drained from the tank. So it's a rate, so it's d something dt. Which one is it? dv dt. It doesn't specifically say the rate at which the volume is changing, but we can tell by the units, cubic feet, that's volume per minute. So dv dt is, again, we're draining, so we want to use -3 cubic feet per minute. And then we got to think about what we need to find. We are finding how fast the water level is dropping. Now, they didn't use the word rate there, but they're talking about how fast. So that's talking about a rate, right? So it's dh dt, because the water level would be the height of the water, right? They could ask us about dr dt. They did not. So we're finding dh dt when h equals 6. Now, here's the problem. If I look at my equation, I've got an r and an h. I've got two variables. I could take the derivative of this, and I would have a dr dt and a dh dt. Do you see a dr dt anywhere? Do they tell us what r would be? They do not, right? So I really want to get rid of that r for this. So if I could have everything in terms of h, I would be able to do the problem much more easily. If I have a dr dt and a dh dt, it might be possible, but it's going to be wretched. So for this, a property that we need to understand is that as the water leaks out of this tank, we can think of the cone that is formed by the water being our like little cone, and then the tank is the larger cone. Because what we're seeing is we're just like shrinking this down, those two cones are going to be similar to each other. Okay? So you're going to retain the like same shape, just a smaller size, as the water decreases in the cone. So the ratio of the radius to the height will remain the same, like the ice cube for the last one. So what we can do, because the cone of the water is going to be similar to the big cone, is we can set up like a proportion for this, for ratios. So like the ratio of the radius to the height, so ratios can be written as fractions, r over h, is always going to reduce to 5 over 14. Right, or be equivalent to 5 over 14. If I take the radius over and divide it by the height at any point, I should still get 5 over 14 because the cone is going to be similar to the big cone. Right? So, if this is true, then I could solve this equation for either r or h. But in this case, I want to solve for r because I want to replace r. right? So all I've got to do to solve this for r is just multiply both sides by h. And so r equals 5 over 14 times h. And so in this formula, v equals 1/3 pi r squared times h, I'm going to replace my r with 5 over 14 h squared. And I'm going to multiply that by h. I would turn everything into a fraction here. I'm going to put this one over 1. I'm going to put this one over 1. I'm going to put this over 1. Everything a fraction, right? Because I can simplify this a lot, which is going to make the derivative much easier. So you could technically do like a product rule or something here, but if you simplify, you'll have actually a very simple derivative. So we replaced the r right here with the 5 over 14h, but you still have the h in the volume formula right there. No, because we have not taken the derivative yet. We are just converting this formula to be one variable right here. So eventually we're going to take the derivative, but we have not done that yet. Good question. So I'm just going to keep fractions right here. I got 1/3. I got pi over 1. I got to square this. So 5 squared is 25. 14 squared is going to be 196. Double check myself here. Yep, 196. And then I've got h squared over 1 because I square the h that's on the inside of those parentheses. And then I got h over 1. I'm going a little overkill with the fractions here just to make sure I keep everything straight, but it helps me a little bit. Straight across the top, I'm getting 25 pi times h cubed. On the bottom, I'm just going to break out the calculator here. 196 times 3 is going to give me 588. There. This can be written as v equals 25 pi over 588. That might reduce, I don't think it reduces that, times h cubed. All right, I can put that h cubed in the top, or I can put it over to the side, either one. There, easier to take the derivative if I leave it over there to the side. Now, something like this, I am definitely letting you use the calculator whenever we're looking at numbers like this, but you might be expected to give an exact answer, not a decimal answer. Well, not really, because even if they do give an exact answer on a multiple choice question, you can type it in to see the decimals for those. You could go decimal right here if you want. It doesn't matter. I like to wait till the end to do the decimal. It's up to you. So, everybody okay here? If you can make it to this point, it should be easy from here. Because this is a simple derivative. 25 pi over 588 is a number, right? It's just a number. So I'm doing dv dt is going to equal 25 pi over 588. I'm just going to leave that out front. Derivative of h cubed is 3h squared. But what do I need with it? dh dt. If you want, you can put that stuff together. I think I'm just going to, I'm going to leave it like it is. It doesn't matter if I simplify it right here or not. I'm just going to go ahead and start plugging numbers in. So I've got to plug in all the values that I have from 2. So dv dt is -3. So I've got -3 over here. I got 25 pi over 588 times 3. And then the h that I'm plugging in is 6. And that's squared. and then that's multiplied by dH dt. Now at this point, I think I'm just going to go decimals here, because I got to do 25 pi over 588 times 3 times 6 squared. So I'm just going to type that in and go for the decimals. And all of this stuff right here, whenever you type it in, should be 14.4257 times dH dt. And then you just need to divide by that 14.4257. And I'm getting negative 0.207962 for my dH dt. You might see a cone problem that is not calculator active, but if you do, it'll be easier numbers for that. It won't. I don't expect you to see something like this. Yes. For this, height is measured in feet, and time, it was minutes, wasn't it? I'm pretty sure. Yep. Time is measured in minutes, so we're looking at feet per minute. There. So, the ladder hitting Adam in the head, because they generally try to stay away from violent scenarios that might trigger someone into a panic in the middle of the test. But all they're going to say is at what rate is the height of the ladder changing at 8 equals 6 or something. But why do you need to know that? In my case, you need to know it because this ladder is going to hit Adam in the top of the head. And we want to know how fast it's going. From that, you could probably also calculate the force to see, is this a detrimental blow or should Adam be able to take it? Don't know. But we're about to find out. So, we have a 20-foot ladder is leaning against the building as shown above. These ladders sliding down the wall problems, or some version of them, they show up a lot too. Okay? The bottom of the ladder is being slid away from the building at a rate of 1.5 feet per second. Okay? Adam is 6 feet tall and is standing below the ladder. There's his first mistake. Next to the building. At what speed will the top of the ladder be traveling when it hits Adam in the head? Okay? So, for whatever is happening, usually it's sliding, but I don't know if it would actually be a constant rate in that case. The bottom of this ladder is moving away from the wall. And that is causing the top of the ladder to slide down the wall. So, we want to know dVdt. Not dVdt. We want to know the rate at which this is changing. So, we're looking at a right triangle here. We want to call one of these sides A, one of these sides B, and we'll call this side C. Right? It does not matter which side is A or B, but C needs to be the hypotenuse. And we're going to write an equation for this particular case. And in this case, it is Pythagorean theorem. A squared plus B squared equals C squared. Okay? So, we want to identify variables that are constant, variables that are changing, and then what we need to find. So, in this case, do we have any variables that are constant? The wall is is going to be constant, but it's not part of our triangle. Same thing for Adam. Adam's height is constant. I don't know, unless it gets like hammered into the ground, maybe like a cartoon would. But Adam's height is constant, but is Adam's height part of our triangle? Is it A, B, or C? It is not. So both the wall and Adam's height are constant, but they're not A, B, or C. So we're not concerned with them. So as A gets pulled away from the wall, is A changing? A would be the distance from the wall to the bottom of the ladder. That's changing because the ladder's getting pulled away from the wall, right? B is changing, but C is the length of the ladder. And this ladder is 20 feet long. Does that change? It does not. C is 20 feet, and it's always going to be 20 feet. So we can actually plug that in before we take the derivative. We also know that the rate at which A is being pulled away from, or the bottom of the ladder is being pulled away from the building at a rate of 1.5 feet per second. So A is getting longer at 1.5 feet per second. So dA dt is going to be 1.5 feet per second. Changing, we've got A and B. A and B are both changing. The ladder length is constant. And we need to find, we are looking for the speed of the ladder when it hits Adam in the head. So a speed is a rate, a specific type of rate, where it can't be negative, even though velocity will be negative here. So is a rate of what? D what dt here? dA dt we already knew. That's how fast A is getting bigger, right? dB dt is going to be it's going to be the velocity of the ladder. Since they said speed, we want to make sure we give a positive answer for that. We're going to say dB dt, and that's going to be when the ladder hits Adam in the head. And Adam is 6 feet tall. So B, like it's going to hit Adam in the head right here whenever B is 6, right? So when B equals 6. Technically, because it's speed, we really want the absolute value of dB dt. If you want to go that far to worry about it, or you can just consider it there at the end. There, all you're going to do is we're going to get a negative velocity because the ladder is traveling down, but speed doesn't have signs. So we can plug our constants in. So 20 can be plugged in. So I've got a squared plus b squared equals 20 squared. Now, I can convert the equation to one variable if necessary. I might should change these notes to be like two variables, right? Like, I want only one variable on the side. In this particular case, if you want, because we're solving for dB dt, you could move that a squared over to the other side right there. But two variables is okay, right? I don't want more than two variables, because if I have more than two variables, when I take the derivative, then I've got like a dA dt, a dB dt, and a dC dt, and I don't know all those pieces, right? So, in this case, we don't need to convert anything. If you wanted to, you can move the a squared to the other side. I'm not going to mess with that. I'm just going to leave it where it's at. We want to take the derivative of the equation with respect to time, right? So if you can get to this point, it's usually not too bad on the derivative. We got 2a dA dt plus 2b dB dt. And that is going to equal, what's the derivative of 20 squared? That's a 0 right there. Because 20 squared is just a constant. Okay, so now we can plug all our values in. So I've got 2. Oh, I'm going to run into an issue right away. I know dA dt. Right? I'm going to use my highlighter here. dA dt is 1.5. I know it. I know b is 6 at the point that we're concerned with. I don't know dB dt, but that's what I'm trying to find, so it's okay that I don't know it. What's missing? What do I not know? A. So I've got to have A because I can't find dB dt unless everything else is a number, right? How could I find A? Plug it into the original equation, because we are only concerned with this particular instant where we know that B is 6 right here. The ladder has hit Adam on the head, right? Poor Adam. I don't know what A is, but I do know that the ladder's still 20 feet long. Right? That's the time that we're looking at, that we care about. Well, if I've got that triangle, it is very simple for us to find A, right? It's just A squared plus 6 squared equals 20 squared. So A squared plus 36 equals 400. And we're going to subtract our 36. A squared is 364, is that right? And then, is that going to be a whole number? No, we get a, so square root of 364 is 19.0788, right there. So now we've got everything that we need to plug in, right? Because we got this piece right here that can be plugged in for A. So we are just going to plug in and solve. So we have 2 times 19.0788 times the ADT, which was was 1.5, plus 2 times 6 times dB dt is going to equal 0. 2 times that 19.7088 times 1.5 is going to give us 57.2364 plus 12 dB dt. We're going to subtract our 57. So now I got 12 dB dt is negative 57.2364. We're going to divide by 12. And so dB dt is going to be negative 4.7697. This is velocity. The question asked us for speed, which is just going to be positive 4.7697. What are our units for the problem? B is the length of the side. What's that measured in? Feet. And then what was the dt? That's change in time. What were we measuring time in for this problem? Seconds. So the ladder is traveling at a speed of 4.7697 feet per second whenever it hits Adam in the head. And if you needed further calculations, you could see what type of force that was.